In section 6.1, we're going to discuss vector fields. So we can have vector fields in 2 or 3 dimensions, or even in higher dimensions. But for this course, we'll only focus on 2 and 3 dimensions. So a 2-dimensional vector field is a function that assigns to each point in the plane, so an xy coordinate, a 2-dimensional vector. And similarly, a 3-dimensional vector field assigns to each point xyz in space a 3-dimensional vector. So here, for the 2-dimensional vector field, you can separate the components as separate functions like this. And similarly, for a 3-dimensional vector field, you can separate the components like this. So sometimes the different components are given the letters P, Q, and R, right? So this component would be called P, this would be called Q, and for a 3-dimensional vector field, this would be P, this would be Q, and this would be R. So vector fields are very useful to represent various physical quantities, right? So like, for example, the vector at each point can represent the strength of some force. So if you have a massive object, it could be a gravity field. If you have electrical current, this could be an electric field. And if you have a magnet, the force vectors could represent magnetic force. Or we can also use vector fields to represent velocity, right? So like, for example, wind speed at each point, or water current at each point. So vector fields are useful in representing these various physical quantities. To calculate vector fields, or to graph vector fields, basically you just take the given coordinates and plug it into the vector field function and just calculate as you normally do. So again, for a 2-dimensional vector field, the output should be 2-dimensional vectors, and here the output should be 3-dimensional vectors. So let's take a look at an example here, right? So we're given the vector field where the first component is y, the second component is minus x, right? So this is P, this is Q. So again, to calculate various points in the vector field, you just plug in the coordinates, right? So when x is 0 and y equals 0, right? So just plug it into the function here, right? So y is 0, so that means that this coordinate is 0, and then x is 0, so negative 0 is 0. So the output vector here would be the vector 0, 0. And if we want to draw it, the vector, right, so on top of the point 0, 0, we have just the 0 vector, so there is no vector here. And then here, if we take the point 0, 1, so y is 1, so the first component would be 1, x is 0, minus 0 is just 0, so at the point 0, 1, we have the vector 1, 0. So we locate the point on the plane, right? So the vector, the point 0, 1 would be here. And then at this point, we draw the corresponding vector that we calculated. So the vector 1, 0 is horizontal and points in this direction. So that's the vector that we get. And then we do similar for the other vectors, right? So the calculation here, y is 1, and then you have minus x, so minus 1 becomes positive 1. And then again, you locate the point, so negative 1, 1 is here. And then at this point, I draw the vector 1, 1. So it will be a diagonal vector like this. Okay, so here the vector is 0, comma, minus 1. So at the point 1, 0, which is this point here, I draw in the vector 0, minus 1, so it's a vector pointing down. And then finally, this last one, the y coordinate is -1, and then negative x would be -2. So at the point 2, -1, so that's this point here, I draw in the vector -1, -2. Right, so -1, -2 would be a vector that points in this direction. Okay, so so that's how you would draw in a few vectors in a vector field. However, it's very tedious to try to calculate the vector for every single point. So this is just demonstrating how you would calculate some of the vectors, but this here is showing the entire vector field. However, typically when you graph these vector fields, so I mean, when you actually graph the vectors, the length of the vector should correspond to whatever the output is. But in these types of graphs, what they do is they shorten the individual vectors, because you can imagine if you're trying to draw many of these all over the place, the vectors are going to start overlapping, and then it's very hard to read sort of how the vectors are flowing. So typically a graph would draw the vectors like this, but shorten them so that the vectors don't overlap each other. And we can use an online tool like GeoGebra to help us graph vector fields. So for example, again, if we want to look at this vector field, right, so we just open up the website for GeoGebra and look for 2D vector fields. Right, so here we type in the components separately. Right, so the first component is y and the second component is minus x. So so the first component is y, the second component is minus x, and then you can see here it draws in the vector field, and so you can see that the flow is sort of circular like this, going in a clockwise direction, and that mirrors what's shown in this diagram here. Except they didn't shorten the vectors as much in this diagram, but if you want to sort of, you can lower the scale so that if the vectors are overlapping too much, and so you can use a tool like this to visualize vector fields. So let's take a look at a couple more examples. Here in example 2, we have this vector field. So x over the square root of x squared plus y squared, and then y over the square root of x squared plus y squared. So let's visualize it using the GeoGebra again. X over square root of x squared plus y squared, and then y over square root of x squared plus y squared. Okay, so you get this vector field where they're all pointing away from the origin, and one thing you can notice is that I mean, maybe it's hard to see or not, but all the vectors have the same length, because here we can actually calculate the length of a vector field by just using the magnitude formula that we're familiar with. Right, so here, say this is p and this is q, that would be just square root of p squared plus q squared. Right, so just plugging it in and trying to calculate, we can see what we get. So this component squared plus this component squared, so we get x squared over x squared plus y squared over So in the denominator, the square and the square root cancel, so you get x squared plus y squared. And then just putting it together, you get x squared plus y squared over x squared plus y squared. And then they just completely cancels out, so you get 1, and square root of 1 is equal to 1. So you notice that, this is independent of x, so that means x and y. So for this particular vector field, every single output vector has magnitude 1. Okay, so that's the second vector field here. And then finally, we can try to visualize a three-dimensional vector field. So a vector field like this is sort of to represent, say, the gravitational vector field. So a diagram is shown here, but again, we can use, say, the GeoGebra tool. Now we need a 3D vector field. So I would just put in notice how they use P, Q, and R for the components, right? So minus x over, and in the denominator, x squared plus y squared plus z squared. And then that whole thing raised to the 3/2 power. Let me just copy and paste to save time typing it out. This was minus y, and this one was minus z. And so this is the vector field that we get, right? So everything is pointing at the origin, and the vectors have larger magnitude the closer to the origin that you are, right? So you can see they get smaller as you get farther away, and so that's supposed to represent that the gravitational force is strongest close to the mass, but as you get farther and farther away from the mass, the gravitational force gets weaker. Okay, so these are some examples of vector fields. Again, to visualize the vector field, it's helpful to use a tool like this to try to visualize it.